Hello and welcome back. We will continue now with chapter 6. This will be the second part of the lecture for chapter 6, and we're going to pick up now section 6.4, resistance banks and strings in series parallel. So to solve series parallel or combination circuits, it is important to know which components are in series with one another and which components are in parallel. Remember, the series component must be in one current path without any branch points. In other words, the components must be on the same line, one after another one, with no other branches coming out of the segment. To find particular values for this type of circuits, we will have to reduce and combine the components using the rules for individual series and parallel circuits. So if we have components that are in series, we need to reduce that to one component by finding the total amount. And if we have components that are in parallel, we also need to reduce that to one component by finding the equivalent component. Reduce the circuit to its simplest possible form. So by doing this reduction and combination of components, we will reduce the circuit to a very simple form in which we can apply Ohm's law to find the values that we need. Let's take a look at an example here. In this circuit, we need to find the currents and the voltages in figure 6.5, which is this right here, right? So the first step will be to find the total resistance. Total resistance, in other words, can we replace this whole circuit by one that has only the voltage and one single resistor? And then we're going to calculate the main line current, so the total current. So if we have those components, then we can just apply those numbers or those values to the different components, and we can find the voltages and currents for different branches and different components in the circuit. Okay, as you can see in here, let's start by solving. Let's start by reducing this circuit to the simplest form. In this case, the first thing we need to do is to identify this bank of parallel resistors. We have two resistors in parallel that can be reduced into one resistor. Okay, so we're gonna keep everything else the same. So we got this one, that one, and this. We're gonna keep that, but this bank can be reduced by finding the equivalent resistance for that bank. Okay, so if we take this portion right here and we apply the knowledge that we already have about how to find the equivalent resistance of two resistors in parallel, in this case it's R3 parallel with R4, we will multiply R3 times R4 and then we divide by R3 plus R4, and we will get a single equivalent resistor of 6 ohms. Okay, notice that this is 12 ohms and this is 12 ohms right here. When we get the equivalent resistor, remember the equivalent resistor for this bank must be less than the smallest one of the resistors in parallel. In this case, they're both 12, so we have to come up with something that is less than 12. In our case, it is 6. Once we have reduced the circuit to this, now we notice that we have, in this branch, we have two resistors in series. So we can reduce these two into one resistor that will be in parallel with this R5. As we do it right here. See that? This 4 ohms and 6 ohm can be reduced to a 10 ohm resistor. So now we have this branch in parallel with this branch right here. So we have this one is R5, and we're gonna call this new resistor here R13, just to give it a name. Okay, and I'm guessing this number came because we combined R6 and R7, so we named the resultant R13. Okay, but this is just the name of it. Now we have this one and that one, R5 and R3 in parallel. So we apply again our knowledge about how to calculate equivalent resistor when we have two resistors in parallel. Okay, we multiply R5 times R13, and then we divide by R5 plus R13. And these resistors are both 10 ohms, so we should get a resistor that is less than 10 ohms, and in our case was 5 ohms, right? So we replace these two by one equivalent resistor that is 5 ohms. Now we have reduced our circuit to a simple loop that has 3 resistors in series. So because they're in series, we can always add them up. Okay? Remember, resistors in series can be added up, and we can replace that with a total resistance, which is equals to the sum of all the resistance. So we have 15 ohms plus 5 ohms, that makes 20, plus 30 ohms, that would be 50. So this circuit, this original circuit, is equivalent to this simple circuit right here. Okay? Now we have reduced our circuit to its simplest form. Having it in this form, we can calculate what is the total current going into the circuit by simply dividing the voltage divided by the resistance. So 100 ohms, 100 volts divided by 50 ohms will give you 2 amps. And this will be the resistance in the circuit. In other words, I'm sorry, not the resistance, the current, okay? So now we have a current that goes into the circuit, and this current is 2 amps, okay? So now if we know that the current is 2 amps, we can calculate the voltages on these resistors. Remember, the voltage, according to Ohm's law, the voltage equals the current times the resistance. This is series components right here. These are series components, so the current will flow in that direction if we take that convention, right? So now we know that the current is 2 ohms. So we multiply 2 times 30, and that will give you 60 volts. 2 times 5, that will give you 10 volts. And 2 times 15, that will give you 30 volts. Notice that these series components, each one of them has a voltage drop of 30, 10, and 60 respectively, okay? The sum of all the voltages must equals the total voltage. Because they're in series, we need to add the voltages. So 30 plus 10 equals 40 plus 60 equals 100. Okay? So now we know that there is 30 volts across this one right here. We have 60 volts across this one right here. So right here, between this point and this point, we have the difference, which is 10 volts. Okay, so the difference between A and B will be 10 volts. So these 10 volts must be the same on this one and this resistor, because these are 2 branches in parallel. If we know that the voltage drop across these 2 terminals is 10 and these 2 branches are in parallel, so the voltage must be the same, 10 and 10. Okay, so we have 10 volts here, and then 10 volts must be distributed across this section of this branch right here, right? Okay, let's see if we can do these calculations again. And we're going to see what we did here on paper, okay? All right, let's see. Here's the circuit. Okay. okay? The original circuit. Again, to replace this bank of parallel circuit into one single resistor, we're going to do the formula for parallel resistors or parallel components, okay, which is R3 times R4 divided by the sum of them two. R3 plus R4, that would be 144 divided by 24, and that gives you 6 ohms. And this 6 ohms, this is equivalent to this single resistor right there, okay? Then we reduced this branch right here, because I have two resistors that are in series in this branch. So R6 plus R7, R6 plus R7 will be 4 plus 6 equals 10 ohms. So I can reduce these two resistors into one single resistor here of 10 ohms, and I'm gonna call that R13, okay? This 13 is just the name of that I'm giving to the resistor, okay? So now, before I mess with these two right here, I need to take care of this bank right here. Now I do have a bank of parallel resistors. Just like I did up here, I'm going to do the same operation here. I'm going to multiply this times this, then divide it by the sum. So R5 times R13 divided by R5 plus R13, which is 10 times 10 equals 100, and 10 plus 10 equals 20. 10 divided by 20 equals 5. So I can replace this bank of parallel resistor by one single one of equivalent resistor of 5 ohms. All right. Now I have 3 single resistors in series. Because they're in series, all that we have to do is add the values of all 3 of them, and we can replace this circuit by a single resistor circuit with a total resistance of 50 ohms. All right. So this simple circuit is the same as this big circuit. Okay, it's equivalent. All this is equivalent to a total resistance of 50 ohms. The voltage doesn't change because I didn't mess with the voltage at all. I just kept it on the same position, so it's going to be always the 100 volts. Now, once I know the voltage and the total resistance, I can just find the total current. The current will be the voltage divided by the resistance, and that will give me 2 amps. So I know now that the current in here is going to be the current going this way, or that way. It's the same current. This is going to be 2 ohms, 2 amps, okay? Now these 2 amps are going to be split going this way and that way, okay? After some mathematical calculations, we can determine that in here, we know, well, actually, let's do it right on this one right here. Okay, this one will get split this way, these two in these 2 directions. Okay, so it will be proportional. If you see this right here is 10 and that's 10, so these 2 amps will be one go this way and one go this way. Okay, because the resistors are the same, so the current is going to be split on equally. And once we know that the current that goes in here is 1 amp, we can take a look at this right here. Now I know that this current equals 1 amp. When it gets here, this one again gets split. Some go this way and some go that way, but I know that it's only 1 amp going this way, and these 2 resistors are the same, so I can say that this is going to be 0.5 amp and 0.5 amp on each one of these branch. Okay. And this 1 amp, it will again come back this way, and this will be 1 amp again, because it's placed right here, but then they get together in here again, and then they go this way, they get added up, and the same 1 amp that goes here comes out of here on this end as 1 amp, and the current in this section right here will be 1 amp. So if we need to calculate the voltages across each one of these resistors, all we got to do is multiply the resistance times the current. So this is 0.5 times 12, this will be 6 volts. 12 times 0.5, that would be 6 volts across this resistor. I know that this one is 1 amp because 1 amp goes in here and 1 amp comes out of here, so that would be 1 amp. So 1 amp times 4 ohms, that would be 4 volts. We already determined that this one also has 1 amp going this way, all right? So 1 amp times 10, that will give you 10 volts here. Okay? So this one is 10 volts. And then this 1 amp, when it gets to this point right here, gets combined with this 1 amp that comes this way, and then back here you will have 2 amps. The same 2 amps that came on the original right here, they get split it different ways, but at the end, when it comes back here, it's the same 2 amps. So 2 times 15, that will give you 30 volts here. 2 times 60, I mean 2 times 30 will give you 60 volts. Okay, there's 60 volts across this resistor, 30 volts across that resistor. And remember, on this one is 1 times 10 equals 10 volts. This is 10 volts across this resistor. All right, so 60 plus 10, that's 70, plus 30 equals 100. That's the total 100 ohms right here. Okay, so hopefully that helped. And now let's take a look at this second example. Another example here. All right, so on this one we have a circuit that has 2 branches in parallel, right? This branch is in parallel with this other branch right here. The source is 90 volts. It's a total voltage or applied voltage of 90 volts. Here is the total current, but this current gets split here between current 1 and current 2. All right? So this current will come like this, but at this point it will split. This is going to be going this way, and this is gonna be going that way. Okay, now to calculate the current, we will have to find the resistance, the equivalent resistance, or we can also find the values here without getting the current, the total current, by calculating the individual current branch, okay, branch currents, right? Let's say, for example, we don't want the total current. We don't know what the total current is, okay? But we know that these 2 branches, okay, this branch right here and this branch right here are connected to this point. Right, so they are in parallel. And remember that we said before that when you have branches in parallel, the voltage across each branch is the same. Right, so in other words, this 90 voltage between this point and this point, we have 90 voltage applied, so it will be the same 90 voltage that are between this point and that point on this branch, and between this point and this point on this branch. All right, so the 90 voltage go through this, are dropped on this branch, and they also dropped on this branch. So if I know that there is 90 voltage across this resistor, so I can always take 90 divided by 30, and that will give me this current, which is 3 amps. In here, I know that I have 90 volts across this branch, right? So if I add these two, 20 plus 25, that will be a total of 45 ohms resistance. So if I divide 90 by 45 ohms, I would get a current 2,3, which is, because R2 and R3, the current on this branch would be 2 amps. So now I got 3 amps plus 2 amps, that would be a total current of 5 amps. Right? So that's one way that you can use to calculate the current on this circuit. But let's see if I can show you this on paper. All right, here is the here we have the same circuit. All right, I got 30 ohms, 20 ohms, and 25 ohms right here with a source of 90 volts. Because these two branches, this branch and this branch, are connected in parallel, I know that the voltage across each one of the branches is the same as the source. So I got 90 volts going through here, 90 volts going through there. All right? So if I want to know what's the current going through this branch, so I take the resistance and the voltage and then divide the voltage by the resistance. I know the voltage is 90 volts, so I divide 90 volts by the resistance of 30 ohms, and that will give me 3 amps. All right, so I1 equals 3 amps. All right, now what about the second branch? They're connected in parallel, so the voltage is the same in both of them. So there's 90 volts across this branch as well, right? However, these two branches, these two resistors are connected in series here. I can just add them up, and that will be the R2 plus R3, that the total resistance on this branch, and I know that the voltage is the same as the applied voltage, which is the same as the voltage on the other branch. So I do, to find this I23, and again, this is just the name of this that I'm giving this current, okay? I say this is I1 because it goes through the resistor 1, and this is I23 because it goes through resistor 2 and resistor 3. Okay, this is just a name. You can name that whatever you like. Okay, so the current on this branch will be the voltage divided by the total resistance, which is 20 plus 25 equals 45. So 90 divided by 45 equals 2 amps. So this current I23 will be 2 amps. All right? So now I know that the total current must be equals to the sum of the branch currents. So that would be, this would be 3 plus 2 equals 5 amps. So the total current is 5 amps. Okay, so I1 is 3, I2 equals 2 amps. So the total would be 3 plus 2 equals 5 amps. So what is the voltage across the resistor R1, this branch right here? Well, we already know because it's in parallel, the same voltage that is here, it must be the same voltage here, right? So the voltage 1 in here have to be equals to the applied voltage of 90 degrees. And the voltage 2, all right, the voltage 2, which is the voltage on this branch, we know that have to be the same, right? But let's prove it. So the voltage is the current times the resistance, all right? So the current I23, we already know, is 2 amps, and the resistor equals the total resistance right here. Okay, but let's do it by parts. So the voltage 2, the voltage on this resistor is going to be the current, which is the same current across both resistors, times the resistance. So the current is 2 times 20, that gives you 40 volts. So that would be 40 volts across this resistor. The voltage on resistor 3 will be the current, which is the same current. Again, this branch has one current of I23, which is 2 amps, times the resistor 3, which is 25 ohms. So 220 times 25 equals 50 volts. So you got 50 volts across this resistor and 40 volts across this resistor. Okay, and if we add them together, 40 plus 50, that gives you 90 volts. In here, across this branch is 90 volts, which is the same across this one, and it's the same as the source, right? That will give you 40 plus 50, give you the 90 volts across this branch, which is the same as the 90 volts on the applied voltage. Okay, Another way you can solve this problem is by finding the equivalent resistor. Let's do it that way. If this is my original circuit, I can reduce this circuit to the simplest form, which would be like this, okay? I'm gonna keep that one for now, right here, and then these two resistors are I'm going to add them up to get the total resistance in this branch. So I will have 20 plus 25 equals 45, okay? So I can replace this with this, a 30 ohms resistor in parallel with a 45 ohms resistor. Now I have two resistors in parallel. I can apply the formula for these two resistors in parallel by multiplying 30 times 45 and then divided by 30 plus 45, and that will give me 18 ohms. So the whole thing can be replaced with a total resistor of 18 ohms. If I know that I have 90 volts in here, to find the current, okay, the current on the circuit, I divide the voltage divided by the current, which is 90 divided by, let's see, 90 divided by, if this is, yeah, 90 divided by 18 will be 5. So 90 divided by 18, so the current will be 90 divided by 18 equals 5 amps. You see that is the same 5 amps that I got on the other side, right? All right, so, and if, let's say I wanted to get this resistor without going through this process. So if I know the current is 5 already, the total current is 5 and the total voltage is 90, so I can just divide 90 divided by 5 and that gives me 18 ohms. See, it's the same 18 ohms that I got through this process. Okay, so as you can see, it's just a matter of recalling and remembering how to calculate resistors in series, how to calculate resistors in parallel, and how to apply the Ohm's law that we learned back in chapter 3 of our textbook in the previous course. Okay, remember Ohm's law says that the voltage equals the resistance times the current, or the current equals the voltage divided by the resistor, or the resistance equals the voltage divided by the current. All right, so here's the same calculations that we just did on paper. And as you can see, we came up with the same 5 amps for total current. We got 3 amps for current number 1, 2 amps for current 2 and 3. And we found also the voltages across B1, B2, and B3. If I know the current that goes in here, I multiply the current times the resistor, and that gives me the voltage on this resistor. Or I should say the voltage drop across this resistor. If I know this current, which I believe it was 2, I multiply 2 times 20, and that gives me 40 volts here. 2 times 25 gives me 50 volts here. 50 plus 40 gives me a total of 90. All this has 90 volts across, all right? 90 volts, which is the same as the 90 volts here. In here, we will also have 90 volts because this current is 3 amps, so 3 amps times 30 gives you 90. As you can see right here, I1 times R1 gives you 90, and for V2, which is this right here, is gonna be this current times this resistor. See, it will be 2 times 20 gives you 40, and then for V3, which is this current times this resistor, and that will give you 2 times 25 equals 5, all right? So, and 40 plus 50 equals 90. What is the total resistance? Again, as we calculated, this is the total voltage divided by the total resistance, the total current. And that would be 90 divided by 5 gives you 18 ohms. That would be the total resistance. All right? So, hopefully this section, this example helps us to understand better when we analyzing circuits that have a combinations of series and parallel components. Okay, it is important to review chapter 4, which talks about series components, and chapter 5, which is about parallel components. In order to successfully solve the problems on this chapter, the problems on the homework, we need to make sure that we understand the two previous chapters, which is the series and the parallel circuits, because this chapter 6 is a combination of chapter 4 and chapter 5. So please make sure you do the homework and do the homework for chapter 4 and 5 before you start working on chapter 6. If you have questions, please let me know and send me an email, or you can call my office, or you can let me know during the lab session, okay? All right, so section 6.6 of our textbook talks about the Wheatstone bridge. This is just a circuit that is used to determine the value of an unknown resistance. The unknown resistor Rx in this case is in the same branch as the standard resistor Rs. Notice right here, this is one branch. This is one branch right here. Here is another branch. These are two branches that are connected in parallel because they are connected through the same or common connection points, right? We know, if we know R1 and we know R2, and we know that the difference between these 2 points, okay, is 0, then the ratio of R2 and R1 must be the same ratio as Rs and Rx. Using algebra, we can solve the problems, okay? So the resistor R1 and R2 form a ratio arm right here, R1 and R2. We can do a ratio here, and I will explain that what it means, okay, in a few minutes. So the galvanometer M1, which is this meter right here, is a sensitive current meter. It's connected between the output terminals C and D. As you can see, this is just a meter, okay? This is the circuit. Here is a meter that you can connect between this point and this point. And then when R1 over R2 equals Rx over Rs, the bridge is called to be balanced, okay? So in other words, when the bridge balance current is in M1 equals 0. So this is a meter, all right? When this measurement from here to here, the current here is 0, that means the bridge is balanced. In other words, that this branch is equivalent to this other branch. So therefore, the ratios must be the same. So R1 divided by R2 must be the same as Rx divided by Rs. So if we don't know this resistor right here, Rx, but we know these two right here, we can adjust Rs in a way that when we do this operation right here, okay, results in the same thing. So if we know this one and these two, we can always find Rx. So using a Wheatstone bridge to measure an unknown resistance, Rs is adjusted for 0 current in M. So connect the meter right here between this point and this point, and then adjust this resistor, okay, either that way or this way. So increasing or decrease the value of this resistor until the meter gets to zero amp, when there is no current going through here from here to here, okay? So the voltage division between Rx and Rs is equals to that between R1 and R2. Okay. So this is the algebra right here. Just remember, if we have this measurement right here equals to zero amps, there's no current here. By adjusting this, so we connect this meter right here, and then we adjust Rs until this is 0, then we can use these ratios. The ratio 1 equals to the ratio 2. So Rx over Rs, it must be equals to R1 over R2. So when we solve for Rs, by multiplying both sides by Rs, then we get the Rx, which is this unknown value, equals to Rs times the ratio of R1 over R2. Okay? So this is one type of circuit that is used to determine an unknown resistor here. Okay? If we have these parallel connected branches, if we're missing one of these, we can always do the ratios. Okay? And that's because remember that if these are these two branches are connected in parallel, all right? So the voltage here across that one have to be equals to the voltage on this branch, which is this voltage right here, right? So therefore, the ratio of these two resistors must be equals to the ratio between these two resistors. Okay, and this is how you calculate it. So they're just the ratio. Basically, this is called a proportion, all right? So two ratios equals to each other form a proportion. And the last part of this chapter 6-7 is about troubleshooting opens and short circuit in short in series parallel circuits. In series parallel circuits, an open or short in one part of the circuit changes the value of the entire thing. Let me show you an example. This is let's say this is the original circuit, all right? Without this, let's say this is the switch, okay? This is just a line there, a wire, okay? So if we don't have this right here, this is open, so the circuit will have this branch in parallel with this branch, and we will have an equivalent resistor here that will be in series with these resistors, and we will have a value there, right? However, if we have a short in a series parallel circuit, the total current and total power increase. If I close this switch, okay, we close this switch to go like this. This is a short. Basically what this does is the current, remember what I said before, the current always like to this way out, so it's not going to go through here. When you find this short, the current is going to just go like this and come back this way. Okay? Basically this whole section of the circuit gets eliminated because no current is going to go through there, because here we have resistance and the current don't like the resistance, so the current will always go through the path where there is the least opposition to the current, and there is no resistance in this wire, so ideally, so the current will just this part short this part out, and then the current will make this loop and the circuit gets reduced to this circuit right here. All right, so They say that the current and the total power increase, of course, because I have 2 amps on this circuit because I have this resistor and this resistor here, so the current is going to be 2 amps and it's going to go and split it this direction and this direction right there, and then come back here. The same 2 amps will come back here, and then we'll continue through this resistor, right? This will be the loop of the current. See that? You're going to go through here, here, and here, and the current will only be 2 amps. You have 100 volts. Once you get the equivalent resistor for this circuit, you will get a resistance that is, whatever the value, it will be more than 10 ohms. So divide that by, basically this part right here will turn into a 40 ohm resistor plus 10, that would be 50. So 100 divided by 50 gives you 2 amps. However, if we close this right here, and we eliminate this part of the circuit gets reduced to this amount. Okay, now we have 100 volts across a small resistor of 10 ohms only. So 100 divided by 10 equals 10. See, the current went from 2 to 10. So if you do a short on a circuit that has series and parallel components, your current will increase, because when you short something out, you eliminate part of the circuit. All right? And the power, of course, remember, the power is the multiplication of the voltage times the current. So in this case, we have 1,000 watts dissipation of power here on this resistor. Okay, and here it is. So you close the switch, then your current goes up, your power goes up. Here's another example when you have an open circuit. This is the original circuit, all right? And now the switch is here. This is closed. That's right now. All right. If you break this wire or this connector right here, you break it and you open it, what you're gonna do is you're gonna have this break in here. There will be no current going in this part of the circuit at all. So this whole thing has no current going through, so no voltage is going to be dissipated in this, and therefore your circuit gets reduced to this right here, this section right here, okay? Because this break right here will have no current. So if you have no current, the whole thing is going to be all the voltage will be dropped around across these 2 points, and no current will flow. See, you have 100 volts here. These 100 volts have to be distributed between this resistor and this resistor only, not on this one, because there is no current here. So if there is no current, no voltage can be dropped on this resistor, because remember, the voltage equals resistance times the current. 80 times 0 is still 0. Okay? So these 100 volts are, they will go 11 here and 89 volts here. Okay? So this is it. 100 equals 89 plus 11, that's 100. No current go here, no voltage goes across. So if this is in parallel, we can say the voltage across this point and this point is 89 volts, which it will be the same as this point and this point. Okay, we will have 89 voltage drop across these 2 points, but no current. So basically, in this case, we can say that this part of the circuit is gone. If we open this, that won't even count for anything. All right, and that is the end of chapter 6. Once again, I'd like to thank you for your attention and for the opportunity to serve you. If you have questions, please do not hesitate in contacting me by email or in person. And our next exam is going to cover chapter 4, 5, and 6. So please make sure that you do the assignments in the same order. Do chapter 4 first, then chapter 5, and then chapter 6, because 4 is about series, 5 is about parallel, and chapter 6 is about a combination of series and parallel. So please make sure you do chapter 4 and 5 before you get into the assignment problems for chapter 6. Okay, again, thank you, and we will see you in the lab session.